In this video, I'm going to give you an example of the second derivative test. So in the previous video, we looked at this surface and we managed to identify the critical point. It turned out to be x equals -4, y equals 3. So x -4, 1, 2, 3, 4, y positive 3, 1, 2, 3. So the critical point is somewhere around here. And when you put this and this into here, it will jump to the surface. I don't know what the surface looks like. Let's just imagine it's this. So it will jump to the surface, and we need to identify if this point here is a local minimum, or if it's a local maximum, or if it's a saddle point. In order to identify that, we need to perform what's called the second derivative test. By the way, there's another one here, inconclusive, but we're going to ignore this inconclusive part. So in this video, I'm going to talk about the second derivative test. Well, the second derivative test is this thing here. But I'm going to summarize it to this. So I'm going to summarize it to this. So what you do is you execute this thing here. Find this value here. If it's bigger than 0, well, all these three are the same here. You find this value here. If these conditions are true, then it's going to be a local max. If these two conditions are true, then it's going to be a local min. And then if this is true, then it's going to be a saddle point. And there's another one, inconclusive, but we're going to ignore this. Well, performing the second derivative test is very easy. Developing, well, the proof is what's important. The proof is what's important. We're going to look at the proof of this, and it's very clever how they came up with this test. Getting to this test is what's important. Executing it is easy, but in this video we're just going to execute it. We're just going to perform the test. In some of the later videos I will look at the proof, and it's very clever how it's done. Well, anyway, let's just execute the test. So we need, well, all these three are the same. So let's just find the value of this block here. So we need fxx, and we need fyy, and we need fxy. So looking at our surface, let's find fx. So fx equals this, xx equals this, fyy equals this, and so on and so on. Remember, our critical point from the previous video was given by this. So now we need fxx. Remember, we need to evaluate it at this point here. So this block here would be us doing this. fxx, evaluate it at -4, 3. So you would put this into xx here, but there's no x over here. You would put this into the y, but there's no y over here. It's just simply the number 2. So that goes in here. So this becomes 2. Looking at fyy is this. Remember, we need to evaluate it at -4, 3. So we would put this into the x, but there's no x. We would put this into the y, but there's no y. It's just simply 2. And then we would look at this, which is here. It's always going to be 0, so let's just put 0 in there. And then square it would be 0. Overall, this whole thing here equals 4. So overall, this whole block here equals 4. This equals 4. This equals 4. So you can see that 4 is bigger than 0. So this is not going to be true. It's not going to be a saddle point. It's not going to be a saddle point. This is true. This is true because 4 is bigger than 0. So it could be a local max. It could be a local min. So what you do is you look at this thing here. So we need to execute this and this. So going back down to here, x-axis this thing here, we need to evaluate it at we need to evaluate xx evaluated at -4, 3. So put this into the x, but there's no x. Put this into the y, but there's no y. It's just simply 2. So going back to here, this block here is the number 2. This block here is the number 2. Well, 2 is not bigger. It's not smaller than 0. So this is not true. This is not true. So it must be a local minimum point. It must be a local minimum. So if you plot the surface into a graph plotter, it will give you this, and you can see it is a local minimum. And the concavity. Just note that the concavity is always positive, which we're going to use when we look at the proof of the second derivative test. Okay.